Okay, so welcome back once again. Hopefully, yes, you have recovered all right from the dreaded problem set 4, and you're already having lots of fun with the new problem set 5. Just to update you on where we are today. So this is, for anyone who is asking, this is our next to last, our penultimate class of this semester. So next week we'll have our last class of the semester. The week after that it's a holiday, and we wouldn't have class anyway because I only have 10 lectures planned for this semester. So this is next to the last one this semester. So right now we're up to right about here. I went ahead and grayed out the last 2 topics because I don't think we'll do those this time. We might do those towards the end of next semester, but they're pretty advanced, so we don't really need to do them at all. So today we're going to finish up. Remember last time we just talked about the keyboard input and timing stuff in theory. So we're going to finish up the demo that was going to address that. Then we'll go back to the lecture for a bit. We'll talk a little bit about reading and writing files and see how far we get with that. So basically, today and next week we're going to finish up the reading and writing files, and that will be everything, I think, for semester 1. So as far as problem sets and things go, everyone should have gotten back problem set 3 late last night, around 2 in the morning probably, when I got around to sending it. And the key to that is also posted along with what you got. So that's in the class folder. I didn't send you the key, but the key is available for download on the class folder. And actually, due to popular request, several people had asked about when the key to problem set 4 would be ready. So I managed in record time to get the key to problem set 4 out today. So it should actually be available in the class folder right now. It'll still be a while before I get to actually mark your problem sets. Usually what I do is build the key as I'm marking your problem sets so I can anticipate problems you had or discuss those in the key. But I just went ahead and did the key the way I wrote everything. So I might update it later, but there is a version of the key to problem set 4 out now. So if you need to consult that for problem set 5, you can do that. Problem set 5 is due on the 4th, which I think is next, like a week from today, right? So that should be the day that we have class. And then there will be one more due on the 14th. That one will be pretty easy. It's just sort of catching up and maybe adding some files and things in. And just to forecast, if you do everything well on problem set 5, there may be a payoff in problem set 6, okay? So this is all building a little bit towards something. Project proposals, remember, due on the 18th. And again, I think people are probably coming along well with that, but if you haven't stopped by to chat with me about your project, might be a good thing to do. Just to let you know, for people that are doing cognitive tasks, you of course don't have to run the experiment. This is just to show your coding skill. You don't have to collect any actual data or anything, because that was one question. And again, these proposals don't have to be anything really anything fancy. But if you guys have looked at problem set 5 yet, there are some questions on problem set 5 asking you basically to, in one part of the question, I ask you to outline what you think you will do when you actually get to writing code in the next part of the question. And that's sort of what I'd like you to do in your project proposals is basically 5 or 6 paragraphs, a few hundred words, a couple pages of a reasonably detailed outline of how you think you will do your project when you get around to coding it. So that's taking into account what modules you'll need, how many trials you'll want to have if you're doing a task, how you'll get your stimuli, whether you'll draw them yourself using CyclePy functions or read them in from image files or whatever. If you need to do any randomization, how you plan to do that. Any sort of algorithms you'll need to figure out. If you want to do something like use mouse input or use some other function that we haven't discussed, or read or write files or anything like that. Basically, I want you to discuss what you're going to have to incorporate into your proposal. Okay. So basically, this is for you to sort of be forced to make an outline of what your code will be in your project, and for me to assess whether that outline is sort of a reasonable project for next semester. Okay, and I know I've pestered you about this in a couple different ways, but for you guys and for anyone listening at home, only via podcast. I'm talking to you directly now. There are some podcast surveys available online. The link to those will be on the YouTube site, in addition to in that notes page that's on our class folder. This is mostly for my PGCHE, my postgrad education certificate project, to sort of assess how well this podcasting idea is working, but it's also so that I can actually try to improve the podcast. So you guys that are here now will take the one for people taking the live class. You guys taking it only online can take the one that's marked for podcast people only. And again, that's not mandatory, but I would appreciate it, and hopefully it will lead to better podcasts later this year and next year. Okay, any questions about other stuff before we get started today? Other questions about the problem sets or projects or anything? All right. Okay, so let's proceed on. So let's do some demo type stuff. So we're finishing up last session. So basically, remember, we had this psychophysics demo that we ended up with where it was this dumb little task where we're judging sound frequencies. But we're going to modify the demo a little bit and also add in some timing and keyboard stuff this time. So that's where we are right now. So, and again, this might be a good one for you to follow along in PsychoPy, but if well, actually, you don't have some of this code, so you can either follow along or not as you see fit. But I will make this code available at the end of today's session, except for a couple things. So let's see. I don't want to scroll too far down here. Yeah, okay. Because one of the functions we're going to use today, if I scroll down just enough, I'm taking a chance here. One of the questions we're going to be using, or one of the functions we're going to be using today, is a function called choose random value, which is part of your problem set 5 homework. So I've already written my version. I've carefully buried it at the bottom of this functions file so you can't see it. Yep, there it is. Okay. So anyway, we're going to use one of those today. But here's the psychophysics demo we had last time. Okay, so remember, we had this set up where we defined some things like how many trials we want, the minimum and maximum frequency, and we used all the stuff we've learned so far to play these two random frequencies or the same frequency twice. The person does a judgment to tell you whether they're the same or different frequency, and they do that several times, and the task exits. Okay. Now again, this is not a particularly good task, but you could see that if we just made it a little bit smarter, this is getting back to kind of that numeric guessing game, right? So you remember that guessing game we did for several demos. The dumbest version of the guessing game we did was just picking, random numbers between 0 and 100, and you had to, keep guessing until it, or the program had to keep guessing until it got it right. This is kind of like that with a psychophysics demo. So, this is, if we just did this and recorded all the answers, it would take a very long time for us to figure out what a person's threshold is for what differences between frequencies they can reliably detect, right? But you can imagine that we can make this slightly smarter and have it narrow down the difference between the frequencies every couple of trials until we got a very exact value for the smallest difference in frequency a person can detect, right? So this is edging towards a real-life psychophysics experiment. And we're probably not going to get to make a real psychophysics experiment out of it by the end of the semester, but we might touch on finishing that up next semester. So you can kind of see how we're building towards a real task. But what we're going to do today is modify it first from being a sound task to a visual task. Again, just so you can kind of see how easy it is to kind of switch between different tasks if you've got things coded up well, and also add in what we talked about last time, which is timing and timing reaction times via keyboard input. Okay? So the first thing we're going to do is we're going to change this from a task playing pairs of tones. We're going to make this a task where I show you these shoe stimuli that we have. This is, again, the dumb shoe task. So I'm going to save this as Psychophys Demo 2, but I'm actually going to save it in this folder with all the shoe stimuli in it, because we're going to want to use those shoe stimuli again from problem set 4. So the first thing we'll do is modify the instructions. So let's say I'm going to show you some pairs of shoes. Your task is to tell me, and what I'm going to do in this time is change the brightness or the contrast actually of the shoes. Your task is to tell me if they're the same or different contrast. Press any key to continue. That's the same. Press the S key if the, let's say the contrasts are the same. Press the D key if they are different. That's the same. Press any key to continue. Do your best. Here we go. Oh, let's actually change that from do your best to try to answer as quickly as possible. Because in this task, we're going to actually not just look at accuracy, but look at reaction time. Okay, so that's all good. That'll be the same. So let's look at what else we have to change to make our tone task into a shoe task. Well, actually, one thing we're going to have to change is the critical value. So we're no longer going to be talking about hertz, right? We're going to be talking about contrast values. And in PsychoPy, the value that we're going to use is going to range between 0 and 1. So maybe we might want to cut out 0, which would basically be no contrast whatsoever, and exactly 1, which is complete full contrast. So let's maybe set our minimum. Let's change it to like minimum value just to be a little more general. Change that to 0.01. And change our max value to 0.99. So that'll be between 1% and 99% contrast. You'll see how that comes in just a minute. Let's see what else we have to change to make this into a visual task. So we're still going to make a window. We're still going to show the instructions just like before. So this stuff can all stay the same. We're still going to do n trials, number of trials, and a loop. So that's fine. All right. So let's change a couple things in here. So if random.randint 1 and 2 equals 1, that's not going to be the same tone twice now. That'll be the same contrast for both shoes, right? And then let's change this from frequency 1 to something like value 1. You could also call it contrast 1, but what I'm trying to build here is build towards a generic psychophysics task that you could use for any kind of psychophysics judgment. So let's just call it value 1 to be generic. And this is where we're going to use that choose random value function that you guys are hard at work on in your problem sets, which I have already written in PsychoPhysFuncs 2, which we're importing. So choose random value, and we want it to be between min value and max value, right? So that'll choose a contrast for the first shoe, and then if they're the same, then value 2 is just going to be set equal to value 1, like it was for the tones. And the correct answer will be S, because they're the same. Otherwise, we need to pick two different contrasts. And again, we'll do this with choose random value. So let's just copy that. So choose random value, choose random value. Again, I think I mentioned this before. There's a tiny bug in this, which is a small percentage of the time, the two values chosen will be identical or nearly identical. But we're going to ignore that for now. So again, a better thing to do would be to make this whole algorithm smarter and gradually narrow the range until people, were right above chance at distinguishing the two contrasts. But we'll forget about that for now. Oops, so I got an extra parentheses in there somehow. There we go. All right, so we picked two different contrasts, so that's fine. And now what we're going to have to do is we're going to change this, get rid of this present sounds function. And we're going to draw the shoes instead. And to save time, I was going to put this in a function so you could see how easy it is to swap in functions. But just for speed, let's put it right here in the loop right now. And then we'll worry about how to functionize this at some later date. So this is all stuff you know. So we're going to be pretty quick about it. So draw the shoes is my comment here. So what we're going to do is, oh, actually, I guess I kind of lied. Maybe I did put this in a function. Yeah, what do you know? All right, so yeah, let's actually call a function I wrote. I lied to you. I did put this in a function called draw shoes. My window, value 1, value 2. So basically, we're going to need to write a function that draws two random shoes with two different contrasts. And so we can go ahead and write that now. And again, I'm going a bit quick because this is all stuff you've done. The shoe drawing thing is almost identical to what you did in problem set 4, but with a small difference in that we're going to have two different contrasts to the shoes, okay? So this is hopefully review for you, or if you didn't quite get this in problem set 4, you may get an example of it now. So what we need is a function called, draw shoes, that takes in a window, the left image contrast, and the right image contrast. What did I forget? Colon, right? All right. And this is going to be very similar to what you wrote in your problem set. So we'll set a variable called number of shoes equal to 195, because that's the number of shoes. Let's call this x position equals 200. This is just saying how far to the left and right we're going to draw it. That's pretty similar to the position we used in the problem set, I think. So basically what we're going to want to do is, let's say, pick a shoe number. And actually, this time it's a little bit different because we'll probably want to show the same shoe at two different contrasts, because otherwise you can't really tell the difference between contrasts if we're changing the shoe. So let's say shoe number is equal to random.randint, a random integer between 1 and in shoes. And if you didn't know how to do this in the problem set, you're going to get the answer now. So if we want to figure out what shoe file to use, we're going to basically say shoe. You remember they're numbered. If we look in the files themselves, they're numbered shoe 001 PNG, shoe 02 PNG, etc., right through shoe 195. And if you wonder why I'm obsessed with shoes, this is from a real experiment we once ran. So these are not like fake stimuli. These are actual stimuli we used for one experiment I did. It wasn't about shoes. It was just about objects, but we were using shoes as one example. So this is a real example of something you might encounter in a problem set. So you're going to use this code, this placeholder with a colon and a 03D, which basically says this is placeholder number 0, which means when we do the .format thing and plug in the shoe number, this is the first placeholder, and actually will be the only placeholder. And then the colon 03D means it's going to be a decimal number with 3 digits, and if you need to fill in any digits, like if you've only got a 2-digit number, if you need to fill in an extra digit, use a 0 as the placeholder, as opposed to a space or something like that. Okay, so it's that, and then we actually need to remember to add the .png file extension to the end of that string. That'll give us a string that's our shoe file name. Then we can create psychopy image stems for the left image, just psychopy.visual.imageStem. Hopefully you guys are pretty used to making these by now, so we'll go pretty quick. So image will equal shoe file, and the position will equal, if it's going to be on the left, we actually need, if we want it 200 pixels to the left or right, the left one has to be positive or negative. Negative, right? Because negative is to the left. So you can actually just say negative x position. Now let's just put it in the center y in terms of y. Now here's the real trick. This is using a new feature of the psychopy.visual.imageStem object. There's been a parameter that we've been ignoring called opacity. So we'll fill in opacity equals left contrast. So what that means, so opacity means if you had like transparent things, right, how opaque it is. So a 1 or 100% would normally mean it's fully opaque, like you can't see through it at all, right? But what this basically means is, since our background is gray, if you decrease the opacity, that gray background shows through. So decreasing the opacity is the same thing as decreasing the contrast. Does that kind of make sense to everybody? Sort of? All right, so again, so in other words, since we've got gray background. If you guys can remember back to your second year cognitive stuff, which I remember you were all paying tons of attention during perception then. Our visual system is highly based on contrast, right? So, if you have just sort of a flat gray background, that's no contrast at all, right? And then white and black are deviations from that neutral gray, right? So basically, if you have something that's got a range of white to black, but then you make it transparent on top of a gray background, that basically, if you make it partially transparent, that equates to reducing the contrast. Does that kind of make sense to people? If not, you'll see kind of how that works in just a second. So basically what we're going to do is use the opacity as a measure of contrast here. Now we're going to do the exact same thing for the right image, except we're going to replace two things on this line of code. Who can tell me what two things we want to change here in this line of code? I think I heard. The opacity has to be that, right? Oh, I think I heard them both, right? The opacity needs to be changed to right contrast, and this needs to just become positive X position, right? Okay, so then all we have to do is do left image.draw, right image.draw. I'm going to leave the window flipping out for now, and you'll see why that is in just a second, because we're going to do that back in our main function, or our main script, rather. All right, and that's all we need to do. So we've got a function to draw the shoes, so that's good. So now what I'm going to do, before we add in all the keyboard and timing stuff, let's just make sure it works. So let's do my window.flip out here, which will actually display what we've drawn in the background buffer. Let's see, what else do we have to do? Do we have to do anything else? Let's see. So we prompt the key press. Oh wait, right, there is one thing we have to do. We have to make the stimuli appear for a certain amount of time, right? So we will actually have to incorporate some timing here. So let's put some variables up at top telling us what our timing is. So let's say our let's call it our stimulus duration, or stim duration, equals 0.3, and like all timings in CyclePy, that's going to be in seconds. And let's also add in a blank duration. So like, show the shoes, show a blank screen for a little bit. Let's make that 0.2 seconds. Noticing I'm always putting my units in comments. That's just because a lot of the time you end up switching back and forth between seconds and milliseconds, so this will help you from getting confused. And let's also put a little blank at the beginning of the trial, maybe. So trial begin blank equals 0.5 in seconds. Okay, that's all the main timings I think we'll need. Okay, so now we're going to need to put in some timing stuff to make our stimuli show up at the right times. And if you can remember back to last lecture, if we can go back a little bit, just to refresh your memory. All right, so remember we're going to need clock objects to keep time, right? So there's really only one main method that we need to do, which is myClock.getTime, and that tells us what the time is right now. So we're going to want to set up some clocks and use them to get our timing so that we can show our stimuli at the right times. Okay? Now again, I know I'm going a bit quick through this. Hopefully it'll kind of make sense as I'm explaining it, or as if you review it later on the podcast. But again, this is for you, this is some stuff you'll want to play around with later and on the problem sets. Okay, so what we'll probably want to do is at the very beginning of our task, so let's say before we start our trials, because we don't really care about timing when we're showing the instructions, right? Because timing doesn't matter then. But we'll want to start our timing here after instructions, but before we start our trials. Let's make a clock. We'll call it myClock. We'll psychopy.core.clock. Remember, it's very simple to create a new clock, just like that. It doesn't need any parameters or anything. And let's just remember to import psychopy.core, so we can use that. So we made a clock, and we might want to record for an output file or something like that, our task start time. So if we want to record that, all we do is call myClock.getTime. Okay? Now, because we've just created this clock, task start is going to contain a number very close to 0. But just for fun, let's see what that is. So we could even print that out. Print task start time. And this is going to be in seconds. Oops. Should use single quotes here for good practice. Okay, put a little placeholder here. Dot format. Task start. So that'll show you how many seconds it took between creating the clock and getting the time from the clock, and it's going to be a very small number of seconds. So here's the timing technique I'm going to show you guys. So if you can remember, we talked about this a little bit last time. The tricky thing here is we've been doing all of our drawing of visual stimuli using this buffering system, right? Or I likened it to a whiteboard with two sides, right? And if you remember, the idea is like you draw on the side of the whiteboard that you can see, but not the side the participant can see. So you being the computer or whatever, or your Python. So you're drawing all your stimuli, getting them all ready. So if the drawing goes slowly, the user doesn't see all the individual stimuli popping up one at a time, right? What happens is you get your whole screen ready, and then you flip your board around when it's all ready, and they see the whole thing at once, right? So they don't see you drawing. If you're drawing a bunch of individual things, they just see the whole screen. And then every time you flip, the front side becomes the back side, and the back side is automatically erased for you to draw a new screen, right? So the trick here is, if you're doing anything with critical timing, ideally what you want to do is, you remember your screen can only change every 17 milliseconds or so. Let's say, but that also means if you wanted to update, sometimes you want to update your stimulus on every single frame that the screen draws, right? Which means you only have 17 milliseconds to draw in. Or even if you don't want to draw every 17 milliseconds, let's say you're waiting like 5 seconds to draw your next frame. So because it does take the computer some time computationally, and it's actually kind of slow to draw things, what you don't want to do is if you want to present something exactly 5 seconds from now, what you don't want to do is wait 5 seconds, for example, using psychopy.core.wait, and then start drawing and flip as soon as you're done drawing, right? Because basically what will happen is, let's say I want to present a stimulus exactly 5 seconds from now. So I wait 1, 1000, 2, 1000, 3, 1000, 4, 1000, 5, 1000. All right, and then I go into drawing mode. I'm like, all right, people seen Bob Ross, or is this impression going to completely go over your heads? You're like, all right, I'm going to draw a scene now, and here's a happy little tree, and here's, and I'm drawing all my little stimuli, and I spend maybe 40 milliseconds drawing that, and then I flip the screen, and then maybe it takes another 10 milliseconds for it to become screen redrawing time again for the monitor. Well, now my stimulus is up 50 milliseconds later than I wanted it to be, right? Because it took me 40 milliseconds to draw it, and I was just sitting there twiddling my thumb for 5 seconds. So what you should do, actually, is every time you flip, go ahead and draw the next thing you want to see, and then wait until just before you want to show the next stimulus and flip then. Does that kind of make sense? So if you have any time that you're waiting around, do your drawing during the waiting time, then wait with whatever time is left before flipping. Okay, so what I always do, and this is what I recommend you guys to do, is I always use the same kind of variable every time. I make a variable that I call wait till. You could call it something else, but I like to call it wait till or wait until. Let's call it wait. So what wait till is going to be whatever time it was just now that the last thing showed up, plus whatever amount of time you want to wait. So let's say we want to wait for the trial begin blank time if we want to start in half a second. And what we're also going to want to do is right here when we start the task, we're going to want to do a mywindow.flip to clear the screen, because otherwise it'll still have the instructions screen up after the person pressed the last key. So we're going to want to flip And then whatever time it is when we flip, we're going to want to set our time that we want to flip the next time to right now plus half a second, right? So actually I'm going to want to take, that means I'm going to also want to take this out here. We're going to want to flip some other time. Because this was clearing out the screen when we were making sounds, and now we're going to clear the screen at a different time. Okay, so now what we've done, so we've set a time that we want to wait to, and this is why, if you can remember, when we did draw shoes, we draw everything to that invisible back screen, but we don't actually flip it, right? Because what we want to do is we want to do all our drawing, and then we're going to want to flip, but between our drawing and when we flip, we want to wait until the right moment to show the two shoes, right? And all we have to do that is do a little while loop. And this is how I usually do it. So while we can say while my clock dot get time, so this just represents the current time is less than wait till. So if it's before the time that we want to wait to, we're going to need to waste some time. And I would do this with psychopy.core.wait. But I'm going to only wait 1 millisecond before I check again. Okay? So that waits 1 millisecond and then checks the time again. Now there are various ways you can do this, but I'm going to have you guys doing it this way because it works best with what you're going to be doing in Psych Toolbox and MATLAB next semester. And if you guys remember, there's a problem with our PCs in this lab that we can't get really, really precise screen timing. But if you could get really precise screen timing, you'd be doing something very similar to this. So I'm going to sort of teach you best practice for the real life scenario, even if this is not quite. There are simpler ways that we could do this if you're not worried about super precise timing. But I'm going to show you guys sort of the quote unquote right way to do it if you ever were to do something really sophisticated that needed precise millisecond timing. Okay, so as long as the current time is less than the time we want to wait till, we're going to want to wait 1 millisecond. Eventually that will cease to be true. Then we'll flip the window. And then what we're going to want to do as soon as we flip is set a new value for wait till, which is going to be the previous value of wait till, right? Because that's when we just showed our current stimulus, plus the next amount of time that we want to wait before doing anything else. So right now, that means we're going to use stim duration, right? Because that's, in other words, we want to draw the shoes and then wait for the stimulus duration before we take them off the screen, right? Does that kind of make sense to everybody? So we're going to wait until the end of the stimulus duration. And then what we're going to do next is draw a blank screen. And what you'll see is when we do code like this, you can kind of copy and paste a lot and then just change a few things. So we can copy and paste that a little bit. But actually, we don't even want to draw the shoes. We just want to draw a blank screen, which means we don't have to do any drawing, really. We just want to, while get time is less than wait till, wait 1 millisecond. As soon as that's over, flip, which will draw a blank screen, right? Because we haven't drawn anything, so it will just produce a blank screen. And then we want to wait another 200 milliseconds, so that's going to be our blank duration. So change stim duration to blank duration. Okay. So that's good. And then what we're going to want to do is draw. So the next thing we want to do before, well, sorry, to back up a bit. Before what we were doing is just popping up using this prompt key press function, which if you remember what it does is draw some text on the screen and just waits around until the user presses a key, right? So that's all well and good, but that's not going to let us do very precise timing later on. So we're not going to worry about timing our key press. Well, actually, let's maybe run this and then we'll worry about how to do this with a really well-timed key press. So actually, that's fine, except what we want to do is add the old, let's say, draw probe text. So what we'll need to do is still wait 1 millisecond at a time until it's time to draw the text. So while my clock.getTime is less than wait till, wait 1 millisecond, then we'll get our key press, and then we'll give our feedback and press any key to continue. And I think that should be enough for like a basic version of this task. And then we're going to enhance this a little bit after that. But let's just stop before we get too crazy and just make sure this works. Okay, so here are the shoes. That's they're same, super different. Okay, so here we go. Oh, now we get to play the debugging game. All right, so there's no attribute weight. Oh, you know what? Psychopy.core.weight is not capitalized, is it? Sorry about that. Got very excited with my capitals. All right, is that all of them? I think so. Let's try that again. Okay. Okay, were those the same or different contrast? I think they were the same. Oh no, I was wrong. Okay, watch again. Oh shoot. All right, so we have a bug here somewhere, right? Oh, I know what it is. All right, let's just skip through. All right, anybody know what my bug relates to? So we've got a bug where it's zipping right through the trial too fast. Anybody got a guess as to what the bug is? So I forgot to do something after the probe text, or in other words, sorry, after the feedback is shown. Yeah, so we didn't reset wait till, which is a problem, right? So now it's having trouble catching up. So what we should actually do is after our feedback, we're going to want to clear the screen. So we'll do my window.flip, because we're going to want to make that waiting interval and set wait till to myClock.getTime plus, because we want the, well, we want an ISI, or an inter-trial interval. So let's call that, I think we call that trial begin blank. So trial begin blank. So that'll blank out the screen for 5 milliseconds and also set wait till correctly. So let's give that a try. Okay, were those same or different, we think? I think they were the same. Okay, yeah. Same. Same. Oh, that was different apparently. Okay, you saw those were clearly different contrasts, right? So that's a different. Okay, so now we've got a really precisely timed task, okay? And again, I know I'm going a bit quick, but I want to get to sort of the payoff of this so that you can see how we can start doing this to calculate reaction times. So well, again, we're not doing anything too fancy. We're just using this clock and its getTime function to get the current time and then set up a series of times to wait to before we actually flip our stimuli, right? So it's nothing too crazy compared to what we've done before. It's just that now we're actually worried about when exactly we present our stimuli, not just waiting for a key press and presenting them any old time. Okay, so now what we want to do, though, is not only worry about when our stimuli pop up, but worry about when our response is given, because obviously if we want to calculate response times, we're going to need to know that, right? So what we're going to have to do is now update our code for drawing the probe text. So the probe, by the probe I just mean when it says the probe text was same or different, S or D. So when it displays the text wanting a response, we're going to need to do something to make this pop up at a certain time and then wait for a key press and actually record how long we waited for a key press. So what I'm going to do actually is I'm going to make another function here in Psychophys Funcs 2, which is like a revised version of, oops, sorry, I got my files all funky here. So I'm going to make a revised version of the prompt key press function, which is very similar, but all it does is, well, it's going to draw the text but not wait for the key press, because we're going to do that in our main function. So let's kind of copy this and change it. So I'm just going to call this one draw text. Keep all the same parameters. But what I'm basically going to do is just take out the flipping and the key press waiting for. So all this is really doing is simplifying the process of drawing text for us a little bit. This is just so you guys don't have to create the scipy.visual.textStem every time. This is just doing a function that lets us draw text. So let's change this to draw text to draw the probe text. We're actually going to want to move this now before the waiting, right? Because we want to get our text all ready before it's time to actually display the probe. Then we're going to want to flip, just like we do up here. So we draw whatever you need to draw, wait, and then flip. Now the key thing is, this time we're going to need to do some new stuff in here. Because in this case, what we've done is we've drawn something and we want to wait for a response. We want to time how long it takes us to get the response, right? Okay, so in order to do that, what we need to do is we're going to use the same functions that we used before, but we need to record some timings. So let's make a little piece of code here that says collect response. And again, this is going to be very similar. It's going to use this psychopy.event.wait keys, but we're just going to use it slightly differently than we've used it before. So what I'm going to do is I'm going to set a while loop up and keep checking for responses until I get a valid one. So what I'm going to do is make a little variable called haveAnswer, which is false, and say, well, I don't have an answer. Oops. I'm going to do this thing. And what I'm going to do is use good old psychopy.event.wait keys, which we've used before. And the only thing I'm going to do is go up here and make sure I've imported psychopy.event, so we can use that, psychopy.event. Okay, so at this point in the code, we've got a key pressed, but just to make it a little more sophisticated, well, I'm going to do a couple things. First thing I'm going to do is immediately record the time the key was pressed. Whoops, not psychopy. My clock.getTime. So what this does is gets a timestamp. The instant that you press a key and psychopy.event.wait keys returns, you get the current time, which is the time the key was pressed, plus some tiny fraction of a millisecond probably for it to execute this one line of code. And then we do the same thing we've done before. Remember we do this trick because in theory, this is very unlikely to ever actually matter, but in theory, the person could hit two keys at once. So wait keys always gives you a list of the keys that were pressed. It's almost always going to be a list with just one object, but we still need to get that one object out of the list. So we get the first item from the list, which is the first key pressed, or probably the only key pressed. And we're going to actually be a little more sophisticated than we have been before and say, let's say, if answer equals S or answer equals D, have answer is true. So what this does is this will just keep us from recording a response if it's not either S or D, right? Now, what we can do actually is we have a key press. We have the key that was pressed called answer. We have the time it was pressed. So what we can do now is calculate accuracy and RT, right? So what we can do is, RT is very simple. So basically to get your reaction time, you need to calculate the time the key was pressed minus when the stimulus came on screen, right? Now, we didn't actually earlier, so the time the shoe came on screen is what we want to time relative to, right? So we didn't actually record that, but maybe it's a good idea to record that now. So let's go up here to where we drew the shoes, and right after the window flips and the shoes go on screen, let's make a variable called shoeOnset and set that to myClock.getTime. So as soon as the shoes pop up on screen, this will tell us what time those came on screen. And so we'll just do key time minus the shoeOnset gives us our reaction time. And if we want to put this in it's going to be in seconds. It might be more helpful for us to put it in milliseconds. So we can just say our RT is equal to itself times 1,000, which just converts seconds to milliseconds. And if we want to make it a nice round number, we can use a function called round, which is built into Python, which just rounds the number to the nearest whole number. What's that? No, because it's in seconds. So if you have like 0.5 seconds, you want to multiply by 1,000 to get milliseconds. Yep. No, you run into this issue all the time because you're always multiplying and dividing to get back and forth between seconds and milliseconds. Okay. And now what we can do actually, we could even like add to our feedback text. And this is, if you guys have ever made a feedback object in ePry, you know it's a little bit of a pain. Here it's actually going to be pretty easy because what we're going to do is we've already given some feedback text as to accuracy. If we want to tell them what their reaction time was too, we can do something like this. Feedback text equals feedback text plus, you guys did this in problem set 4, I think, right? You added strings together to create a bigger string. So you can say new line, new line, new line. Your RT was some number or some placeholder, milliseconds. And that's just, and then we'll do that format, RT. Okay, so what that'll do is we've calculated the RT in milliseconds. This will just add to the feedback text and add 3 blank lines, then parentheses, RT colon, and then the number, and then milliseconds. The word, MSEC with the parentheses. Okay, so let's see if that works. Oops, shoot. Raw text is not defined. Why is that? Oh, wait, did I not save this file? Yeah, that's probably it. Okay, we're the same or different contrast. I think same. All right, that was very slow, 5,900 milliseconds. Same? No, that was supposed to be same. All right, so see, it's got my RT as 1740.0 milliseconds. Let's try to respond very quickly. Okay, that was pretty quick, 726 milliseconds. So that's pretty cool, right? So, well, cool for some sense of the word cool. So we've now got our RTs calculated for each trial, right? And actually, if you want to fix this, this kind of annoyed me. So if you want to fix, you notice that what it did, it had a floating point number for the milliseconds, right? And that's or a floating point number meaning it has a decimal point in it, right? That's because key time, myClock.getTime gives you a number with a decimal. So key time is a decimal. shoeOnset's a decimal. So that's a decimal. So RT becomes a decimal or a floating point number. When you multiply that by 1,000 and round it, rounding it just makes it a round number, but it doesn't make it an integer data type. So if we want to turn it into an actual integer, we can just say int. That's a little trick to force. It's called typecasting, but what it really means is you're taking a number that's a floating point number and forcing Python to treat it like an integer. So it just cuts off the non-floating point part. So basically, like in other words, if I said, A equals 5.2, it's 5.2 and there's some weird rounding error. But if you do int A, it's 5. Does that make sense already? Versus round A, which gives you 5.0 but doesn't express it as an integer. So if we want to make that little fix, now we should have a much nicer little display where reaction time is an integer. Same? 1646 milliseconds. All right. So good for us. Different, same, different, right? Okay, cool. So does that kind of make sense to people so far? Any questions about that? I know it's going kind of quick. By kind of quick, I mean probably really quick, right? Does that sort of make sense what we're doing though? So we're just going to, well, actually, maybe we'll stop there for the moment. And then what we're going to do when we come back, so you'll see how this all builds. So what we're going to do when we come back is we're going to incorporate a couple more techniques. We're going to talk about writing files and reading files. And then we're going to use what we know about Python lists and so forth that we've learned in the last few lessons to make a list of all the accuracies and response times, right? Because if you guys run an ePrime task, what you usually do is at the end you get an output file that gives you all the times the stimuli came on screen as well as all the accuracies and response times. So what we're going to want to do is do the same thing, keep a list of accuracies and response times and write out a file at the end that tells our accuracy and response time. So let's maybe take a break. If people have questions about the code that they want to talk about offline, we can do that. And then we'll come back after the break and do a little bit of lecture and then see how the file writing works. So for posterity, so during the break we mentioned one way to get around if you haven't written your choose random value function is you could do something like this, immortalized in this XKCD. You could write a little fake choose random value function like this. So if you want to get your code working, you could do that, or you could just actually write the choose random value function from problem set 5. Okay, so what we've got now is we've got this demo that does some basic timing, gets a reaction time based on these clock functions. So now what we're going to talk about is kind of the last step that I think will let you guys build most cognitive tasks, is we'll talk about files and reading files and writing files. And that's really, I think, in PsychoPy, the last major concept that we haven't talked about at all that you would need to make maybe 90% of all cognitive tasks. So, you know, obviously, if you're doing some really kind of crazy task, you're going to need to employ the concepts we talked about in some pretty sophisticated ways or build some fancy algorithms with them. But the basic tasks or the basic functions and modules and so forth that you'll need, we will have covered by now. So today and next time we'll talk about reading and writing data to and from files. I think we actually, if we keep going at this rate, I'll slow down a little bit, but I think we'll actually have a little bit of extra time next time to kind of debug and talk about the problem set. So that'll be good. I don't think it's worth trying to cover any more topics. Now, it's worth noting that PsychoPy has its own way of logging data from experiments to output files. But I personally, I mean, it's not that I think it's bad, but it's not the way I like to visualize my data. So if you guys want to use this, you can check out this psychopy.logging modules. That's logging as in writing out like a log file, not like as in cutting down trees with a chainsaw. So you can use this, and this is what's used if you run a PsychoPy task through the builder. You get out one of these files. So if you guys have ever used the main interface of PsychoPy, you might have seen these output files. But we're going to talk about something different. We're going to talk about using the built-in Python file writing functions to write your own files in whatever format you want. And what's nice about this is you can design your task then to write out exactly the data that you care about and nothing more, nothing less, and make your analysis much easier. And actually, if you want to, you can even build some analysis right into your task itself and have it just spit out the final results of your run. Now, before we go any further, I do have to warn you of one thing, which is that now it shouldn't be a major concern for you guys, but when you start writing code that can write data to the disk, you stand the potential to do some damage, right? Because what you'll find out is, your code has the privileges to overwrite any file that you have privileges to change on your computer. So, you could do some damage to your system files or your code files or something like that if you tried hard enough. Now, in reality, unless you try pretty hard, you're probably not going to run into that, right? Because what you just have to be careful of is that you realize that when you write files, you can erase files very easily, and that if you don't have the file name exactly right, you're going to erase or write over the wrong file, right? Now, it is unlikely you're going to call your data file for your subjects anything that's remotely the same as a critical system file, right? Like I don't suggest saving any of your subject data in the C Windows System 32, very critical information folder. But so as long as you just call it something like subject543.txt or whatever, you should be okay. But just be warned that you can overwrite data very easily. So this is when you're writing code for real use, this is a very important part of code to debug carefully. Because otherwise, what you don't want to do is, run 20 subjects through a task and then realize you've been writing all the subjects' data into the same file and that you've only actually got the last subject's data, right? So this is something you just want to be careful about. Okay, so that's just a warning. I mean, again, I don't think it's anything we're going to really worry about. And in terms of what we're doing, I don't think we're ever going to try to write a file outside of the directory that your code is in. So in theory, you can't ruin anything outside of the directory that your code file is in. But if you really wanted to, you could probably find yourself a way to accidentally overwrite your code file as it's running or something crazy like that. So just be careful about checking that you're actually writing into the right files. Okay, so just a little bit of background. This is the boring background stuff. Unfortunately, the files topic is not the most interesting topic. I don't have any crazy images because it's just like text files on a computer. But it is pretty cool what you can do with them. But just to let you know the background, there are basically two main types of files in terms of how your computer treats them, which are text files and what we call binary files. So when we say a text file, we mean a plain text file, meaning like something that you can open up in Notepad in Windows or using like TextEdit on the Mac or something like that. So some examples. So that doesn't just mean like .txt files, although .txt files are a plain text file. Like HTML files, for example, if you do any web page editing, those are also plain text files. And your Python files that you write your code into, that's also a plain text file, right? So it doesn't mean it's a particular file extension, but what it means is everything that's in that is just plain text. There's no other information that can't be read as text to the human eye, right? Which contrasts with binary files, which are basically everything else, even if the information in the files is text in some sense. So for example, JPG files or any picture file, your doc files in Word, and your application files. So anything else that doesn't just contain text information is a binary file. So like your Microsoft Word doc files, if you try to open that up in TextEdit, it's just a bunch of crazy random characters, right? It is not human readable text, even though what is stored inside it is information about text you've written, right? Does that distinction kind of make sense to everybody? Everybody knows what I mean. So the main thing to note is that you don't really have to worry about this distinction too much. It's mostly for historical reasons about how different operating systems treat text. And if you tell like Windows something is a text file, it'll open it up correctly even if it came from Linux or the Mac or something like that. It's not really important to know why. The main thing to note is that we are only going to be working with text files in this class, and you should always open text files in text mode and binary files in binary mode, because if you open one up in the wrong mode, it doesn't read quite right. But the good news is we're only working with text mode, and that's the default mode in Python. So as long as you don't do anything weird in Python, we don't need to do anything very special. So that's good. That's just a little thing to kind of keep in the back of your mind, though, that there are these different modes. Okay, so what we're going to talk about first is writing to files. So actually, in a way, it's a bit easier to write to a file than to read a file, although it's very similar. So we're going to talk about how to do that, and then actually, hopefully, incorporate that into our script. So basically, there are a few steps to this. So the first step is to do what we call opening a file for writing. So this is like, when you think of opening a file, you're used to like double-clicking it or going to the file menu and saying open, right? And usually that's for reading a file or also writing into it. But when you're talking about programming, those two things are separate actions. So you can open up a file for writing or open it up for reading, or you can actually open up a file for both, but we're not going to do it that way in this class. We're going to only write a file or only read from a file. So when we open a file for writing, what it does is it creates what's called a file object, and this is with Python. So, It's not a CyclePy thing, it's just a Python language thing. But it creates an object called file object. And the way we do it is like this. So the main function, it's built into Python, you don't have to import anything. So you just say open, and then give it the name of your file, and then you give it the letter W, which is code for write. So this means I want to open a file called this, and I want to do it for writing instead of reading. Okay? Now what that does is it creates a file object, which in this case is called myFile. Now, the key thing to note here is that it doesn't give you any like warning dialog box or something if the file already exists. If you open up a file for writing and it already exists, it just creates an empty file and overwrites the old one, okay? So this is like the case where you have to start being careful, is that there are no warnings. Now, if you want to warn yourself, you can write code to check first to see if this file exists and only open it if it doesn't exist already. But you're going to have to handle that for yourself. And that's a little bit beyond the scope of what we're doing, although it could be a good thing, for example, to incorporate into your project if you wanted to. So that's just something to note. Now, sometimes this is fine, like, if you, like what we're doing today, if we have some bugs or something, we don't want to have to check every time that the bad version of this file is deleted before we write the new version, right? If we're debugging. But, you may want to check things in a final version of a cognitive task. So that's just something to keep in mind. So you don't have to write any data into it. As soon as you open the file, it's assumed to be a blank, empty file, and it gets rid of anything that was already there in that name. All right. And then the way that you write text to that file is very simple. You just say myfile.write. So each file object has a method called write. And then you just put a string inside the parentheses that's what you want to put in the file. So it's super, super easy, right, compared to a lot of things we've done. And then what you do is you write as much data as you want to the file. You can call write as many times as you want to, and all the text just gets added on to the file. And when you're done, you have to close the file by calling myfile.close, okay? So each file object also has a method called close. What that does is basically tells the operating system you're done working with that file. Now, the nice thing is that if your script crashes, or if you quit CyclePy or whatever, you're not going to cause any like permanent damage to your system if it crashes before you can call myfile.close. But in general, you want to remember to close the file, because if you don't close a file, everyone's probably gotten that error message, like when you try to eject your USB flash drive, that it says like, sorry, this file on this drive is in use and I can't eject it right now. That's because some program didn't call the equivalent of myfile.close. So myfile.close is what tells Windows or the Mac operating system or whatever, I am done with this file. It is not being modified anymore. So it's really important that you close it, or else, if you're on a flash disk or a flash drive or whatever, or some other program tries to read the file or something like that, it's going to get error messages saying that the file's in use until you close it. Okay? So that's just worth keeping in mind. Now this is actually, there are other things you could do with files, but this right here is pretty much all you actually need 90% of the time to write files in Python. So the file writing stuff is not tricky, really. It's just sort of like the timing stuff. The actual functions are really simple. Then you just have to figure out sophisticated ways to use them, right? So writing the text is not difficult. It's figuring out it's just like writing an essay or a final year project report or a novel. The actual typing of the code in is very simple, or the typing is the easy part. Figuring out what you want to put in there is the difficult part. So that's what we're going to do now. So what we're going to do is take this last demo, and we're going to write a very simple output file, again, kind of like what ePrime writes, that contains accuracy and reaction time info when the task is done. Now in the process, we might learn a couple of other tricks about Python and CyclePy that we'll need to have in order to do this. So let's give that a shot now. So again, this may be something that you just want to watch, although you're welcome to follow along if you like. Okay, so let's call this, just to save this previous version before we start messing around with it, I'm going to just say this is Psychophys Demo 3. I'm actually not going to change anything in the psychophysics functions file, so I'm just going to close that. And I'm not going to change that to psychophysfuncs3 because it's the same. Okay, so let's see here. So the first thing we're going to probably want to do, and this is one of the first new little tricks that we're going to have to learn, if we want this to be like a real task, we're probably going to want to ask, before we do anything else actually, before we show instructions, before we even create a window or anything like that, we're probably going to want to assign some participant number or subject number to this run so that we can write out a file with the subject number, right? Because that's what E' does. It asks you for the subject number, then it writes out a file with your subject number, right? So we're going to use one other PsychoPy module that we haven't really talked about, but it's pretty easy to figure out what it does. It's called psychopy.gui. That's for graphical user interface, right? Like your operating system has a GUI that makes windows and stuff. And we're going to use something called psychopy.gui.dlg. That's for dialog box, like the little boxes that ask you for information. Because we're going to use a dialog box to get our participant number. So let's say we're going to use psychopy.gui.dialog, and what you do is you first give it a title. So let's call this like participant info, and we're going to have to make an object. So we're going to say like sub info dialog equals that. So that's going to create an object, a dialog box object called sub info dialog, which so far is just going to be an empty dialog box called participant info, like at the top of the window. So then what we're going to have to do is add a field or two to this, like sub info dialog dot add field, and a field is just like a text entry field, and we'll say label equals participant number or label. And I say label because maybe you want to label your participants 1, 2, 3. Maybe you want to label them with their names, which is not very good for privacy, but you could do it, or you could call it XYZ or whatever. All right, so we only want to ask them one thing. Then we're going to want to call this method called subinfodialog.show, which will show the dialog box. And what that's going to do is show the dialog box, and then it's going to stay up until the person either clicks OK or cancel. So there's no way to change that. There's no way to, I don't think at least. So there's no way to take away the cancel button. But so maybe what we'll do is say, so when it's done, it goes on to the next line of code. And then what you have to do is you have to do a check like this. If sub info dialog dot OK, so if that's the case, then we'll make a variable called subject. Let's call it subject label, and that's going to be sub info dialog dot data 0. I'll explain what all this means in just a second. So if they don't click the OK button, that probably means if they click cancel, I guess the most logical thing to do is quit. So you might want to print an error message like user pressed cancel. And then we're going to use another function that we haven't really talked about, but the function of it should be pretty obvious. Psychopy.core.quit. Oops, not quite, quit. Okay, so what that's going to do is psychopy.core.quit is pretty simple. It's just a way to end your task early if you don't want it to execute any more code. So let's just run this and see an example of this in action. So if I run this, it comes up with a little dialog box. You see, so we create the dialog with the title participant info. So that goes here. Then we add the field that says participant number / label and makes a little text field. So I can enter whatever I want to in there. It has already shown the dialog box, and now it's waiting. It's waiting for my response. So we're paused like at this line of code right now. So if I click cancel, it says in my output, user pressed cancel. Don't worry about this weird warning message that just happens for no good reason. It says user pressed cancel, and it quits the task, right? Otherwise, it would go on and run the task if I clicked OK. Now there's a few little things we haven't talked about yet in here. For example, this dialog.data, it looks sort of like a method, but it's actually not a method because there's no round brackets or parentheses, right? This is actually a way of accessing like a variable that's part of the object, which we haven't talked about yet. So we won't get into the real details of that yet, but basically the idea is that this subject info dialog has within it a variable called data, which is a list of what was entered into any text fields. And we want the first item from the list, which in this case is the only text field. So again, it's a little bit of magic that I haven't talked to you guys about yet, but you don't have to worry about it too much for just now. We might go into this a little bit in a problem set. But anyway, all this is effectively done is gotten us a subject ID, so then we can use that to build as part of our file name so that we can write out a different file for every subject that does our task. And by the way, you might note that also the same way that data looks like a method but is actually a variable because it doesn't have any parentheses, it's the same thing here. So OK is not actually a function or a method, it's actually a variable that's part of the subject info dialog. So again, that's probably a little bit more than we need to get into, but that's just worth noting that we'll maybe talk about a little bit later. Okay, so anyway, all that you need to worry about for now is that we've got this variable called subject label or sublabel, which is whatever we typed into that dialog box, which is a subject number or an anonymous ID or something like that. Okay, so generally speaking, there's a couple ways we can now go about writing out a file, okay? So one thing you could do is open up a file when your task starts, and every time you record a response with a reaction time and an accuracy, you could write that to the file and then close the file at the very end of the task when all the trials are done. So one advantage of that is that if your task crashes halfway through, you'll at least get a partial file written out. The disadvantage of that is like it kind of scatters your file writing code all over the place, and if you've got any if your whole task is time critical, writing files to disk is kind of slow, so it might interrupt your timing. So what I prefer to do is just write code that is very solid and will not crash in the middle of the task, and save all my data in variables during the task running, and then write my file at the end of the task. So that's what we're going to do now because it keeps the code a bit cleaner. It's probably a bit easier for you guys, and in general I think it's better practice, but keep in mind that if there's some concern that the subject might end the run early or that the task might crash or something like that, you could be writing out this file all through the task so that when it crashes, the file is already partly written. Okay, but for now what we're going to do is we're just going to save all of our responses as the task runs and then write the file at the end. Now in order to do that, what we're going to need to do is save all of our accuracy and response and our response time information in a list, right? Because we want to maintain a list of the accuracies and the response times for every trial. So I'm going to make a little empty list called all accuracies, another little empty list called all RTs. And what I'm going to do is, just like we've been doing in the problem set so far, which hopefully you've figured out by now, maybe not, we're going to use this append trick to add, every time we calculate a new accuracy or a new reaction time, add this to the list of all accuracies or reaction times. Okay, so where do we get our reaction time in this task? Right down here, right? So once we've calculated a new response time, we can just take our list called all RTs, we call that append function of the list, and add the latest response time to the list, right? So that's just going to make a list of RTs every time it does a trial. It'll add this latest RT to the list. And then what we can do is right here and right here, when we determine whether the person answered correctly or not, here is the case where the answer was the correct answer. So they get the feedback text correct. And what we can also do is add to our accuracies list. We can append. Probably most of the time you want to call 1. This is what EPROM does anyway. Like 1 is a good code for accurate and 0 is a good code for error. You want to make up some code. I mean, you could make it like the word correct or something like that. But usually if you're importing this into Excel or something, 1s and 0s work well. So I'm just going to call it a 1 when the person's correct. and append a 0 to the list of accuracies if they're wrong. Okay? So now what's going to happen is at the end of the task, these all accuracies and all RTs lists are going to have several elements in them, right? One for each trial. And then what we can do down here is go down here to when the task is over, maybe right before we tell the person that the task is over. This is only going to take a fraction of a second, so the person won't have to sit there and wait. But right before or right after we give the task is over message, what we're going to do is write out an output file. Okay? So we have to come up with a format for output file. So let's say our output file name is going to be subject or sub underscore plus. So we're going to build a string here with the plus sign. What do we call our previous variable? Sub label. So plus whatever the sub label is. And then plus, maybe call it something like, data.text, right? So if you put 123 in for your subject number, it'll be sub underscore 123 underscore data.text, right? So that'll be the name of our output file. And then if we want to, if you want to just sort of give an update in your output as to what's going on, you might say something like, you don't have to do this, but you could say like, creating output file. Well, we can do this a couple different ways. Output file name. So that'll display a little creating output file message in the output to sort of clue you in that it created the output file. So now what we're going to want to do is open an output file for writing. So let's call this output file, because this will be the actual file object. This is not just the name of the file. So that'll be our Python open command. We want to open our output file name with the code W, which means we want to open it for writing. And again, that will destroy any other sub 123 data.txt file that you have. So just be aware of that. So if that works, then we're going to do output file.write. And let's figure out what the format of our output file is going to be. So a lot of the time, probably the easiest way to do this is to make what we call a tab-separated file, which, like, you've probably seen text files like this, right, where it's just plain text, but you separate. It's sort of like a fake Excel spreadsheet, like you just separate all the values by tabs. That's probably the easiest type of file to write out. So let's write out that one, because it imports really well into Excel, even though it's just text. So maybe we want to write some headings to the top of the file, so you might write something like, trial number. Now, remember how we used \n before to indicate a new line? \t is going to be our little secret string code for a tab. So trial number, tab, accuracy, tab, RT, new line. So that's going to write in our file trial number, then a tab, then accuracy, then a tab, then RT, and then in the line there, and start a new line, right? So that'll give us our headings. And then what we're going to want to do is loop through our accuracies and response times and write out each accuracy and response time to the file. So this is where we would need a for loop, right? So let's say something like for trial num in X range. I think our number of trials variable is called in trials. So we're going to do this once for each trial. And it's going to be pretty simple. This might look a little funky. So let's maybe build a string that we'll call like line to print or something like that. So what it's going to basically be is a trial number, then a tab, then an accuracy value, then a tab, then a response time value, and a new line, right? And again, we can use this little placeholder format we've been using to build strings all along. So the 0 will be our trial number, and then a tab. Placeholder number 1 will be our accuracy, then a tab. And placeholder number 2 will be our response time, and then a new line, or a return, right? And we just have to call that .format and give it the trial number, which will just be trial num, right? Because that's the variable that's going to go 0, 1, 2, 3, 4, 5, whatever, up to the number of trials. And if we want to be nice and make this human readable so it counts from 1, not 0, we could even add a 1 to it. And then we need an item from our accuracy list, right? So again, this may make, depending on how well you did on problem set 4, hopefully this will make sense. So we have our list of accuracies, and we want to slice it or get one item out of it using this square bracket operator. So it's going to be the accuracy value for that trial number. And then we're going to do the same thing for the RTs list. Get the RTs for this trial number. That's it. So end that with a round bracket or parenthesis. And then all we've got to do is do output file.write line to print, which is just our string that we created. And that's actually it. And then we just have to remember when the for loop is over, we've written everything we need to the file. So we can just say output file.close. Okay. Now let's see what happens if we run this for realsies. Hopefully it will work. All right. So participant number, let's call me 007 or whatever. All right, same task as before. Let's say that same contrast. So this is actually all going to be the same contrast, but it's going to give me a bunch of different answers. By the way, I didn't note this before, but remember when we had it print out the task start time? You see that this is 2.86 times 10 to the negative 6. So this is a couple of microseconds that it takes to run a line or two of code in Python. So this tells you, this timing is, in theory, pretty accurate. But anyway, so it printed out, creating output file, sub 007 underscore data.txt. Now the real question is, did it actually create that file? So if I go to my demos folder, and I had this in the shoes folder, let's see. What did I call this? Sub 007 underscore data.txt. Oops. And if I'm going to open this up, I'm going to use my favorite text editor, Text Wrangler, which is a good Mac app. It's free if anyone has a Mac. Hey, look at that. So trial number, tab, accuracy tab, response time, enter. 1, 2, 3, 4, 5, accuracy 0, 1, 0, 0, 0, and then milliseconds here, right? And you'll see what's nice about that format is if you open it up in Microsoft Excel, Excel knows how to, whoops. Oh boy. I've never run Excel from this user account before. Oh, that wasn't too bad. What? That was weird. Just a second while it updates my font menu, apparently. All right, so I don't think Excel got the message. Let's try that again. Open with Excel. All right, there we go, right? So now I've got a nice Excel readable file, and if I just want to average, for example, if I want to get average accuracy, it was 20% accurate, right? Average RT, right? Pretty easy, was 1157 milliseconds. So you see one nice thing here is, if you guys are used to doing E-prime, you get this file out with all this crazy stuff in it, like most of which you don't care about. One nice thing about writing your own files is you can actually write whatever you want into this file, right? So if I wanted to write the name of the shoe stimulus that was displayed, I can make a column for that. If I wanted to, whatever you want, you can put in this file. Or if you want to, you can write out, like some friends of mine I know write out multiple files, one of which is like the very basic information file that they do for analysis, and one of which gives a whole bunch of information about each trial, just in case they need to go back and see if something went wrong with the task, or see which particular stimuli were on the screen or something like that, right? So any questions about that so far? Anybody got issues or questions with any of that? All right. Oh yeah, do you have a question? Yeah. So that's actually, maybe that's a good thing to do in the next couple of minutes, because because I probably went so fast in the first half, I'm actually going to be able to get to reading files pretty easily next time. So maybe we'll do reading files and a little bit of bonus material to be announced next time. Yeah, you can do that very easily, right? So like I said, one nice thing about this method of doing things is you can do whatever you want to in your actual task, right? So if we wanted to put in an average, and then you don't have to do any analysis at all, right? What we could do, for example, is, the average formula is just the number of things divided by the total, right? Actually, we don't even have to do that. So here's a little trick. So before we close our file, wait, am I giving you anything? What did I ask you to do in problem set 5? Did I ask you to average some stuff in problem set 5? I don't know if I want to tell you. Let's do a quick check to see if I'm going to tell you any illicit information. Because I think didn't I put that in there, or did I only put that in from? I have a plan for problem set 6 already, so I don't want to give too much away. It's 3 of you are looking at this right now. Anybody remember, did I ask you to average any information? Okay, I didn't in problem set 5, right? All right, well, I guess I won't in problem set 6. I don't think I'm giving anything away. All right, so if you have a list, so let's say I have a list like, let's just do a dumb example. So A is the list 0, 1, 2, 3, 4. Lists have some convenient, I thought they did. Oh, wait, sorry. It's not a method of the list. It's a built-in function of Python. So there's a built-in Python function called sum, which will add up all the values in a list. And I think it'll even do some crazy things like this. So, like if we said A equals this is a, sorry, we need commas in here. Sentence. So we've got a list like that. I think if we do sum A, oops, no, I lied. Okay, so apparently sum won't work with strings. It'll only work with numbers. But anyway, if you have a list like, 1, 2, 3, and you do sum of A, it'll give you the sum, right? So it's very easy to calculate the average of our accuracies and RTs. We could say average RT equals sum of all RTs divided by what? You guys remember the function to figure out how many? Well, actually, there's a couple things we could do. You could actually just do n trials, right? Because you should have 1 RT for every trial. You could also have done len of all RTs, right? Because that should be how many there are. So that's just the average formula, right? The sum of all of them divided by how many there are. Now, I'm going to do one little trick here. Both of those are probably integers. So if I want to get a decimal version when I divide, I'm going to multiply the sum by 1.0 first to force it to be a decimal. And if I want to get the average accuracy, this is one nice thing about if I call accuracies, if I call them 1 for correct trials and 0 for incorrect trials, then if I want the percent accurate, it's just the average of all those values, right? The average of all, because every correct trial is 100% correct. Every incorrect trial is 0% correct. So if you average all those, then you get the overall percent correct. So sum of all accuracies times 1.0 divided by the length of all accuracies. And then I could just print those out to the file. So I could say something like output file dot write average accuracy new line dot format average hack. Notice I kind of did something I haven't been doing previously, but I'm kind of building the string inside the function call, right, rather than creating a temporary variable for it, which is something you can do. Whoops, output underscore file, and output underscore file dot write average RT, maybe put some spaces if you want them to line up. Average RT, and then close the output file, right? Okay. I think that should work. So let's give that a try. Okay, so I'm just going to give some random answers here. So let's say number 999 this time. Okay, wrong, wrong, correct, wrong, correct. Let's see how our file looks now. Oops, did I get rid of that window? So if we go in here, whoops, it's in the shoes folder, isn't it? There's some 999 data. Ooh, that's weird. Where'd my RT go? Well, that's funny. Is that something that Excel's doing? Let's see what's going on in the actual text editor. Huh. All right, let's see what I did wrong here. Oh! It's two separate lines, so it's a 0 placeholder both times. Sorry, not a 1 placeholder. All right, let's do 001. Okay, wrong, wrong, correct, wrong. Oh, I'm not very good at this task. All right, so subject 001. Hey, there we go. If we open that in Excel, it should open up pretty nicely. Look at that. So there's our nice little pre-calculated averages that you could just plug right into, you know, SPSS and not have to do any funky Excel stuff, you know, for your analysis of each subject. Okay, so any questions about any of that? I know that was going a bit quick, but again, you'll have the chance to practice some of it, but that gets us through almost everything. So next time we can talk about reading files and maybe a little bit of bonus stuff, or just kind of catch up and do Q&A and talk about projects and stuff. So any questions or anything before we break? All right, well, let's call it a day then.